Sylvia, first one up
Yeah,
here. Did you get a confirmation from the Hispanic scholarship thing?
yeah, I logged in, then it like had a check mark next to the
Perfect.
submitters.
Okay, good. I'm sorry I waited so late to do that, and thank you for reminding me.
Yeah.
It'll be all right, I think. Oh, who we got here? I don't know if there's anything as such as a restful weekend anymore, but anybody have a restful weekend? Everybody have a restful weekend, whatever, lots to do. Not I keep thinking I'm going to take a break, and then I keep thinking of things I need to do. And I think you're right. It seems like there's more to do when you're not at school, but that hardly seems possible, but somehow it's true. All right, we got almost everybody. 1, 2, 3, 4, 5, 6, 7. All right, while we're waiting, guys, I'll put the screen on in a minute, but has anybody got any questions? I've got some answers this morning about when I think the next test is going to be and sort of how the rest of everything's going to play out. So we'll talk about that for a little while, and I'll give you the next we'll answer some questions on the homework if you have it, and tell you what I put on Moodle to help or to try to help. Okay. All right, let me go ahead and share the screen, and then we'll wait for people to come in. Yes, I trust this computer. I've been using it forever. I don't care if there's a new version available. Okay, not letting me say I trust my machine. Ugh. Come on. Let's see here. Guys, I'm going to log back out and try to log back in and I don't know what will happen. I hope you guys stay in, but I'm not, it's not allowing me to move the cursor to say I trust the machine I'm on. Don't know why, because I've been on it for every instant of my life that I've ever been on Zoom. So, make sure, there we go. There we go. Maybe there's just a bad connection. There we go. Okay. Yay. Okay. All right. I think we got almost everybody here. Haley's not here. Let's see who else I've got here. And just about everybody else. She'll be in a minute, I guess. Okay. Let me start by showing you the assignment sheet first, and then we'll talk a little bit about that, and then we'll come back to your homework if you got any questions on that. So guys, this is on Moodle. I sort of backed it up a day so we knew where we were. On Friday we did that. We spent a second day on that method of undetermined coefficients. The handout that I'm referring to there is that practice guessing handout that we started working on Friday. The key to that is on Moodle as well. Okay, so if you remember that what we were doing in this was practice guessing what a particular solution was, and we plugged in our practice and its derivative, practice guess and its derivatives, and we matched coefficients on the individual terms. It's messy, but it's not hard, assuming you make the right guess. So it's really, really critical that you look at this thing and make sure you understand how to make the right guess, that you're making the right guesses. If there are any questions on that, I'll take those in a minute. The homework on this is due on Wednesday. I'd like to have it by class time if possible, so I can get a quick turnaround. Everything needs to be pretty much on time and a quick turnaround at this point, because we're getting sort of towards the landing zone. Okay, we're getting towards the runway of the end here. So I think we've got basically 3 full weeks and a couple of days of classes left. After that, they're in this same chapter, and this has been a long chapter. The sections have been long. We spent 3 or 4 days alone on section 4.1, but if you remember, section 4.1 was setting up things like what's a fundamental set, how do I find it, how it's linearly independent, and the Wronskian and so forth. And we've used all of that stuff, like what a general solution looks like. It's a YC plus a YP. That should be kind of ingrained in hell. The rest of the chapter has been devoted to finding out these techniques, all right? So what we're gonna go on to today is another technique called variation of parameters. The homework is the chapter, is out of the edition 10 of the book. I haven't yet gotten a chance to take a picture of the homework sections in that. I will try to do that and get it up late this afternoon so that when you work on this, you can check your answers, okay? The next thing we're gonna do, and we'll spend a couple of days on this, are something called Cauchy-Euler equations. There should be an S on that. This is the cutoff for the next test, all right? This Wednesday, Friday. Due on Friday will be homework on variation of parameters, the stuff that we do today, right? So you're having a little bit of a lag there, which is what I want. I want to answer questions if you have them, and we have a lag. In a 3-day class, a class lag is one class lag seems like a long time, but it is what it is. Oops, sorry. So that the test will end right at the material right there, but there's one more homework assignment due. There's the one due on Friday on variation of parameters. Again, what I'll do today. There'll be one due on Wednesday on Cauchy-Euler equations, all right? What I will do is try to get that's due on Wednesday. This Monday section right here will not be on the test. I will go ahead and do some things on Monday and Wednesday that will not be on the test. They'll be on the last part of the last test. Will be a fairly short one, but that'll be after the Cauchy-Euler equations. It'll start with systems of differential equations. The test I will give you on Friday, May 1st, okay? And I'll give you over the weekend to do that, and it'll be due the next Monday. Okay, so that's the setup for the next one. So it'll be basically techniques, and I'll outline that for you. I mean, you will have had homework back on all of it. So what I'm hoping is that'll inform what you're doing. It'll be the same as the last one. It'll be open book, open notes, no outside sources, no help from anybody else. By outside, I mean getting online. And I mean, you can find out how to do these things online, but that's sort of misses the point of trying to figure out how to do it yourself. So that's what we're looking at, all right, in the next basically 2 weeks. Okay, questions, anybody about that? Does anybody have a problem or an issue or any questions about that? Okay, anybody have any trouble with method of undetermined coefficients? You may, or I don't know, I can't remember when I put that key up for the guessing method, but you might want to start out there and see if you're guessing properly and then do a few of those. They're long and messy. My suggestion to you would be maybe you don't need to do all of this. Notice that the homework here, as I told you on Friday, it was odd numbers. So you might even want to try starting out on those. Get your guess, try to do those. I said I put odd ones on there so you could check the answer in the back of the book. Even if you've got have I posted those? I'll try to post all these book pages in the book, and I'll post the answer page in the back so you can see for each section what the answers are. Okay. Questions on that, anybody? All right, let's go to what I want to talk about today. Okay, so we did method of undetermined coefficients. That's what we were doing the last couple of days last week. Today we're going to do something called variation of parameters, and it looks a little bit like something we've already done before. And as with a lot of these things in DE, let me see if I can get this thing off of here and move that. All right, so get away. Okay, I'll get it off randomly in a minute. Um, here's what we're going to do. We're going to talk again about second order linear DEs. We're going to talk about non-homogeneous ones. Notice there's this g of x here. When we were talking about the last method, the method of undetermined coefficients, these things were constants. They are still going to be constants. We're not going to get to variable coefficients until those things called Cauchy-Euler equations. But as we know, there's probably Haley or there's Cerrone and Haley I'm missing here. Okay. Sorry, I'm having trouble getting her admitted. Okay. All right. So so we're looking at a similar thing, but what I need to remind you of is when we did this with constant coefficients with the method of undetermined coefficients, this f of x had to look like something very specific. And if you remember it, it's on page 143, if it helps. We had to have an f of x here, this non-homogeneous part, that behaved in a certain way. And the way that it had to behave was that when you differentiated it, you got things like that back. And what we saw was that those things were like exponentials. They were like sine and cosine. They were like polynomials, things like that. We noted right at the beginning of doing that we could not do f of x's or g of x's, sorry, like that. Because when you differentiate the log of x's don't come back. The derivative of log of x is 1 over x. If we had a tangent there, it wouldn't fall into this group because the derivative of tangent is secant squared and you don't get tangents back. So that method that we had of undetermined coefficients was limited because of what g of x could be. Now, the method I'm getting ready to show you today, the variation of parameters, is it's not limited like that. As a matter of fact, it'll work for the things we used method of undetermined coefficients for, and it'll work for functions like this that were not in those sort of get it back kind of derivative forms. So again, for now, we're still going to let the coefficients on the DE be constants. So we will still be looking for a general solution in that form right there. Okay. From all that stuff in 4.1, it said when we're looking at these linear DE, linear homogeneous or non-homogeneous solutions, the general solution has a complementary solution and it has a particular solution. And just again, to remind you of method of undetermined coefficients, the first thing we had to do was find the complementary solution. That's where we had to solve the characteristic equation right there and write that solution to the homogeneous part. And then we had to be careful about the YP that it didn't duplicate anything in the YC. So that's all the big ideas we had about method of undetermined coefficients. Now, this particular method, variation of parameters, is going to abide by this. We are actually going to also need to find the YC. All right, definitely find the YC for use in this method. And we'll have to figure out a way to find the YP. Oops, messed up. Let me get back here. Okay, so so guys, I'm going to suggest on some of this that you just watch what I'm doing because it gets really messy, as with a whole lot of the ways we prove how DEs are going to work. It's messy getting to it, but in that mess comes a method that's not that hard. Okay, so one of the first things I'm going to do in this method is put the equation in standard form. Now, if you remember what standard form looked like, it meant that you had to divide by the coefficient on the highest derivative, all right? So we'll look at that in a minute, but when we did it, we had to do it for linear equations and so forth, but essentially it ended up looking like maybe y double prime plus py prime plus qy equals some, we'll say, function. And actually, since we called g of x the function that we had originally, when we divide by this thing, we're going to call it f of x. So we're going to have to put it in this standard form. I've got that written down below, but I'll write it for you right now. In other words, before you start this method, you need a coefficient of 1 right here. And since we're working with all constants, p and q are also going to be constants, but you've got to have a coefficient of 1 on that. You got to put it in standard form. Okay. The second thing we want to do is try to figure out how we can come up with a YP. And it has to do with something we talked about when we were doing method of undetermined coefficients. Remember when we were doing the guessing method, we didn't want anything to duplicate. We didn't want anything in the YP to duplicate anything that was in the YC. And that meant that we didn't want a constant multiple of it. We didn't want a linear combination of them. We didn't want anything like that. So here's the fundamental thing that's going to make this work in this thing. We're going to guess that YP looks like that. Now, let me tell you what Y1 and Y2 are. Y1 and Y2 are the elements of the fundamental set. They're the pieces of the complementary solution, okay? And so the first thing you will do is get your YC. And the Y1 right here and the Y2 right here are the members of your fundamental set. And in a second order equation, we know there are 2 of those, okay? So what we're going to do to form the particular solution is take that Y1 and Y2 and multiply them by U1 and U2, where they are not constants. They are not going to be duplicates of things in the fundamental set. We don't know what they are, but they are not going to be constants. So if I look down here to what I've written here, it says this replacing of C1 and C2 with U1 of X, and U2 or U2 of X is called the variation of parameters. Okay. Now remember, what's the reason for that name? C1 and C2 are parameters. All right, they're parameters. It's a 2-parameter solution of a homogeneous equation right here, of a second order homogeneous equation. They're called parameters. We've been doing that all along. I'm going to vary those constants. I'm going to make them functions of X instead of constants. Otherwise, we don't have a solution that's going to work. We've got something that's going to get sucked up in YC, and we don't want that. We saw that led to contradictions in the last method we did. Okay, so that's what we're going to do. Okay, any questions, anybody? That's kind of the setup of how I'm going to start. I'm going to put the equation in standard form. I'm going to find the YC that goes with it, because ultimately I'm going to need the Y1 and Y2. So our goal is going to be then to find U1 and U2. Because when I find those, I'm going to take them and multiply them by Y1 and Y2 and work out this YP. You might remember doing this when we did reduction of order back in 4.2, when we had one solution, we were trying to find another one. That was a first order application of this thing called variation of parameters. Questions, anybody? All right,
so before we do the problem, when we put it in standard form,
yes,
you're saying that the only constant that should be in front is 1.
Yeah. Tara, everybody look at this. So getting the D in standard form means I'm going to divide by whatever was here. You know, if it was a 5 or a 2 or a whatever, I'm going to divide by whatever was here, and there'll be a 1 there. And what's left will be the coefficients that we call P and Q, right? And then G of X will get divided by something, and we'll call it F of X. So okay. First step, put it in standard form, get a 1 there. If you don't get a 1 there, you are going to get the wrong answer, okay? Now, here's where I want you to just watch me, guys. I'll just give you a preview of this. So this is why I want you to watch me, okay? I don't want you writing down all of this stuff, and I had to keep myself straight by using my nifty little colored pens to see what I was going to group together. Okay, so let's just watch what I'm doing, and we'll look at what happens. So what I'm going to do is I'm going to start out with this sort of proposed solution, where we took the elements of the fundamental set, multiply them by two functions, u1 and u2. My goal here is to find u1 and u2. I want to find u1 and u2. And I'm going to have to make some assumptions along the way. Whoa, jumping on me. I'm going to have to make some assumptions along the way, but I think in the end, I'll actually be able to find them. And once I find them, I can form this solution. So I'm going to do what I've done a number of times in this course, and that's if I propose a solution, I'm going to take its derivatives, and I'm going to plug it in to see what has to happen to make it true. So let's just look at it. I'm going to use the pointer here, guys, instead of trying to write on this thing. If you look at the YP that we're proposing, you've got a product of two functions here and a product of two functions there. If I want to find YP prime, I'm going to use the quotient rule, the product rule on the first one and the product rule on the second one. So on the first one, I get U1 Y1 prime plus Y1 U1 prime. So that's the product rule on that first piece. All right. And on the second one, I'm going to use the product rule on that one. So U2 Y2 prime plus Y2 U1 prime. All right, so I use the product rule there. And I generated 4 things. So this is a second order equation. I'm going to end up plugging into it, and I'll have a second derivative in that second order equation. So I'm going to take the derivative of that first derivative. Now, you see what's going to happen. I'm going to have to use the product rule on 4 of these terms right here, which is essentially going to double them. So first, U1, Y1 double prime, Y1 prime, U1 prime. So there's that one. Y1, U1 double prime, U1 prime, Y1 prime. There's that one. Use it on this. This times the derivative of that, so right there, plus Y1 prime times the derivative of U2 prime. And then one more time, Y2 times U2 prime, U2 double prime, plus U2 prime times Y2 prime. Now, this is in your book, guys, but they don't kind of carry it out in such detail. They skip a bunch of steps. And because of all the notational things and the primes and the subscripts and so forth, it's a little hard to see. But what I've done here, again, to find Y prime is take the derivative of that. And then to take Y prime, find Y double prime, take the derivative of Y prime. And I get this. Now here's where it gets, again, it gets a little messy. But what happens here is that I'm going to plug it into the DE. So let's look at it right there. So DE, remember, once I put it in standard form, look like that. YP double prime. And again, I'm trying to find a particular solution that'll give me this f of x over on the right, this non-homogeneous part here. So I plugged in YP double prime. YP double prime was the one that was the big one at the end. It was all of that stuff right there. Okay. I think somebody just got bumped out. All right, if you guys see anybody trying to get in, let me know, or hear from anybody. So that first big string of things, there were 8 of them. There they are right there, YP double prime. And then P of X, I'm just going to start writing P, times YP prime, that's the one that had 4 terms. So that's that YP prime. And then the last one, YP, was my proposed solution. My proposed solution looks like U1, Y1 plus U2, Y2. All right, now the tricky part here is something that's used in a lot of these proofs. And it's the fact, something you know about YC. If you plug in a member of the fundamental set. It's a complementary, it's the solution YC that makes, well, that's the solution to the homogeneous DE. And if it's the solution to the homogeneous DE, then what happens is that when you plug it in, you get 0. And that's going to drive my grouping here. So here's what I'm going to do. I'm going to kind of show you. In yellow, I took U1, Y1 double prime, and I took U1, Y1 prime, and I took U1, Y1. And I took all 3 of those because there was a U1 in each of them. And I pulled that U1 out. Now, I want you to note what you've got here. What you've got there is a Y1, which is part of the homogeneous solution. Y1, that was part of the fundamental set. And when you plug that in, you will get 0. So all of those nicely, because this is a big mess, drop out because you plugged part of the YC into the DE. And that was the part that gave you 0. Okay. The next thing I did, if you look at these green ones, can you guys see the color all right on this? Somebody on mic can tell me if you can see the colors. This is the only way I can figure out how to do this. Can you see the colors?
Yes.
Okay, all right, good. All right, so the next one, I picked the green ones here, U2, Y2 double prime, U2, Y2, and there's a U2, Y2 prime. I picked those because they all had a U2 in them. So when I pull out the U2 right there, I end up with Y2 plugged into the DE. Now remember, Y2 is the other part of the complementary solution. It was the other member of the fundamental set that made the homogeneous part true. So if it makes the homogeneous part true, and here's my DE, 1Y double prime, PY prime, QY, Y, it's gonna be 0 as well. Again, because your Y1 and your Y2 are solutions to your homogeneous part, okay? So those 2 parts wipe out, which is nice. Now let's look at what I've got left. I took, and there's reasons for this that we'll see in a minute, the ones in blue that had a coefficient of P on them, I put right here. The ones in, I don't know what this was, rose color, were just a couple right here. And again, you don't really know why I'm doing this, but you'll see in just a second. The other 2 that were in purple were these 2, all right? And the other 2 were these right here, the ones in the, whatever that is, I don't know, purplish color, all right, right there. So one reason I colored them all is so I knew I got them all. So I've got them all here. All that first grouping, those 2 things went to 0. Then I've got 1, 2, 3, 4 pieces left. Okay. So all I have left in here is this and this. Now, there's something else that I need to do. And it drives the reason that I grouped them the way that I did. If you will look at this thing right here, it's the derivative of Y1 U1 prime. Let's check it. There's Y1 U1 prime. So Y1 times the derivative of U1, which is U1 double prime, plus U1 prime times Y1 prime. So I'm gonna look at that and say, well, that's the derivative of that. We don't know why it makes a difference yet, but that it is. This one that I've got in this pinkish color here is the derivative of Y2 U2 prime. So it's going to be Y2 U2 double prime plus U2 prime times Y2 prime. So it's the derivative of that. Now I'm going to group these things together. There's this one. Let's see, is that one? I put those 2 right there. Since you've got the derivative of this and the derivative of that, I just wrote the derivative of this plus that. So that's what that term right there is. It's those 2 put together. Okay. And then I've got the P, which is right there. And then I've got the last one, which is Y1 prime U1, Y2 prime, or Y2 U2 prime. Okay, sorry, Y1 prime U1 prime. It's this one right here. Plus Y2 prime U2 prime. Okay, Now, and it's all supposed to equal to f of x. You know, about this time you're wondering if this is going to ever end, and the answer is yes. But we're going to make some assumptions that will allow us to find u1 and u2. That's what I'm after. If you look at those two things right there, y1 u1 prime and y2 u2 prime, they are both in here. All right, and then there is this one. Here's what I'm going to do, and this seems odd. It seems very random. But I'm going to say, you know what? The quickest way, and you're going to think, how can she do that? But it's just a way that we're going to try. The quickest way to find out what f of x is to look at these two things and say, you know what? They're the same. Why don't I just let that thing right there be 0? Right, now there's a reason for this, but let's just do it first. I'm going to say, well, if I let that be 0, then that drops out, and that drops out. So let me write that assumption right here. I'm going to assume that those two things will drop out. All right, I'm going to let each one of these, let that be 0. Okay, it's the same in both of them. That leaves me with this. So it leaves me with y1 prime u1 prime plus y2 prime u2 prime is f of x. So look at what I've got here. If I make those two assumptions, and again, these are assumptions on the way to a method, in case you're starting to worry, you're not going to be able to have to run through this process for every single DE that we're looking at using this method. We're going to come up with a formula for this method based on these things. Now, recall what we're trying to do. We're trying to find u1 and u2 so we can work out our proposed YP. So we already know those. What we want to find is u1 and u2. Okay, so that's a big assumption that I made, but it's going to allow me to get hold of something I need. So in other words, here's what I've got. This is important right here. Look at that system of equations. That system of equations, let's look at what we know and what we're looking for. What we know are y1 and y2. Because if you remember, y1 and y2 were the members of YC. They were the fundamental set. They were the fundamental set. So we know those from having solved that at the very first of this problem. The variables here are u1 prime and u2 prime. Now guys, if I can find u1 prime and u2 prime, remember what I'm looking for. I'm looking for u1 and u2. If I know u1 prime and u2 prime, all I have to do is take the integral of this to find u1 and the integral of that to find u2. So once again, let me remind you, of my goal in the end is to find u1 and u2. But again, if I can find u1 prime and u2 prime, all I have to do is integrate them and I'll be able to do that. All right, let's take a breath here. Mountain Dew or whatever your choice of drink is. I'm going to die by sodas. Some people die by cigarettes. Some people die by whatever. It's going to be sodas for me. Okay, we're going to go back to high school. Maybe high school. I'm not sure they do this much in high school anymore, but if you've had linear algebra, you probably saw it. Hold on what we're doing right now. I want to talk about something called Cramer's rule. Sometimes it's spelled with a K. That's the German spelling. This guy was German. There is another way to solve a system of equations. Now, if I gave you this system right here, you guys will say, well, I'll solve that by substitution maybe. I could solve for x in terms of y and then plug it back into the other equation. I'd get it. Most of the time we would think, well, maybe I'll solve it by elimination. You might want to multiply through this by -3 so you dropped your x's out. That would work. This is a third way to find solutions of n equations in n variables. You got to have the same number of equations as you have variables. And something else has to be true, and it's this. You do, at least when I do linear algebra, I do a proof of this because it's a very handy kind of thing. First thing I want to do is write it like what we call a matrix equation. So guys, if you remember, it's the row and column thing. 2x minus 3y is 5, and 6x plus 5y is 1. However you want to think about it, this thing right here, this 2 minus 3, 6, 5, is called the coefficient matrix. All right, so it's the coefficient matrix. Okay, so you pick off the coefficients there, and that's what you got. Here's what Cramer's rule says. It says take that coefficient matrix and put it down here in the denominator of a fraction. And that's the denominator of a fraction that's going to give you the value for x and the value for y. And what do the straight lines stand for, guys? What do the straight lines stand for? Anybody, unmic and tell me. We've already done it. Dealing with the Wronskian. What is it? Yeah, it's the determinant. It's the determinant, okay? Now, it's an easy determinant. It's a 2 by 2. So remember how we did that. At least one person was getting this backwards. You start at the top left, you go down, and then you subtract the multiplication here. So this is 10 minus a minus 18. That bottom determinant has a value of 28. Now, nice thing about this Cramer's rule method, in all the variables you're trying to solve for, that bottom determinant is the same. So that was 28 too. You see that I put the coefficient matrix in both of them. Now, here's what Cramer's rule says. And it's a really neat proof, I'm not going to sidestep to do that here. That treads on linear algebra, but I'm going to show you how it works. If you look at this thing right here, the 5, 1, what things are equal to? When you look at a matrix equation, most people refer to it as AX equal B, where A and B are matrices. A is your coefficient matrix, B is this solutions matrix over here. What Cramer's rule says is this. Put this thing, if you're solving for the first variable, put that 5, 1 in this determinant up there. So replace the first column of the determinant you found down here with that thing right there, 5, 1. Then leave the other column like it is. So minus 3 in this case, and 5. Okay. If I'm solving for y, in the y column here, I'm going to put 5, 1 in that one. And I'm going to leave the first column like it was. Oops, didn't mean to do that. 2, 6. So this 5, 1, right, when I was solving for y, it went in the y column. When I was solving for x, it went in the x column. Okay? Does anybody remember this? Who's had, Sylvia, you've had linear algebra. Who else has had linear algebra? I don't know. Do you remember doing this in linear algebra? Unmic for me, Sylvia. Do you remember? You may not have done it. I don't know.
Yeah, I don't remember. I was in linear and I don't remember too much.
So Tara, is that you? I can't. Yes. Yeah. Okay. Well, it's okay. Not everybody's going to know it. Maybe nobody knows it. I don't know, but now you know it. Okay. Again, I'm telling you, it works without any, without any explanation. Dr. Young tells me that's a ticket to math hell, but what can I say? I don't have time to do it. But the point is, guys, you can solve any system of equations here. that's got the same number of variables as it has equations, as long as the determinant of the coefficient matrix is not 0. Can't have 0 down here. So there are some equations you cannot solve, but as long as the determinant's not 0, you can use Cramer's rule. So let's finish this one up. In the top, if I find the determinant, it'll be 25 minus a minus 3, which will be 28, over the 28 that was the determinant in the bottom, which tells me 1 is the x value in this solution. In the top, on the right, let's see, 2 times this will be 2 minus 30, all right, and that's minus 28 over the 28 that was already there, and that's minus 1. So x is 1 and y is minus 1. Okay, we can check it. If x is 1, y is minus 1, you get 2 minus a minus 3 is 5. If this is 1 and that's minus 1, we get 6 minus 5 is 1. Okay, so that's Cramer's rule. Now, because you may need it in a different situation, if you have a 3x3 equation, you'd be solving for x, y, and z. And you do the same thing. If you're solving for x, you'd take the column that's right here, put it in the first column, and the other two remain the same. In the next one, if you're solving for y, put it in the second column, and the other two remain the same. And then if you're solving for z, it goes in the last column, and the other two remain the same. If I have a little time at the end of class, with a few minutes left, I'll show you how to do a 3x3, because you may need to do a 3x3 maybe once in your homework. Okay. Okay, so that's my side step there. Anybody questions about how to use Cramer's rule? You'll see how I'm going to use it in just a second. Okay, so here's my system of equations that I was trying to solve a minute ago. y1 u1 prime, y2 u2 prime equals 0 f of x, or 0 in the top, and then the second one equals f of x. Remember that my variables here are u1 prime and u2 prime. All right, u1 prime and u2 prime. The things that I know are y1 and y2, because they were the fundamental set. y1 and y2 came from your yc. If I write it in matrix form, I get y1, y2, y1 prime, y2 prime, multiplied by the variables, which in this case are u1 prime and u2 prime, equal to 0 f of x. So by Cramer's rule, that's what I'm using now. I'm going to go ahead and use Cramer's rule. I don't think you see this in too many high school courses anymore, because it's not on the end of year test or whatever it is they give now. It's not a lot of time to do everything you need to do. What goes on the bottom, remember, is the determinant of this thing. Now, before we go any further, does this determinant look familiar if you know that y1 and y2 are members of a fundamental set? Anybody? What is that?
A Wronskian.
It's the Wronskian. Exactly. That's exactly what it is. Good. That thing right there is just the Wronskian. Okay. So we'll have that as soon as we solve the complementary part of the equation. What's going to go in the top by Cramer's rule is this. If I'm solving for the first variable, which is u1 prime, I'm going to put in this solutions matrix over here. So right here, I'm going to put in 0 and f of x. And in this one, the second column won't change. It'll be y2 and y2 prime. y2 and y2 prime. In this one, the second variable I'm trying to solve for, I'm going to put 0 f of x in the second column. And I'm going to leave the first column the same. y1, y1 prime. F of x. Okay. So let's look at what I've got. This is actually not hard to set up. And they'll actually have formulas in your book if you want to use them, but I kind of like to see what the setup is. But what we know is that u1 prime here is something over the Wronskian, and u2 prime is something over the Wronskian. And if we find this determinant, this isn't too bad because there's a 0 right there. So if I find that determinant, it'll be 0 y2 prime minus y2 times f of x. So that's u1 prime. If I look at this one, the determinant in the top will be y1 f of x minus, cross this way and subtract, but there's a 0 there, so that's just 0. So the formulas and where they came from are right here, and that's where they came from up there. Okay, I do not, in a normal semester, you'd be working without a net. In other words, you would not get your books and you would not get your notes. So I always just try to set these up because I don't like memorizing formulas. Okay, I like knowing sort of where they came from, and then I can find the formulas easy. Now, remember that what I needed to know was u1 and u2. These two things gave me u1 prime and u2 prime. Now we just need to integrate to find u1 and u2. And then the last step is to form the YP and the general solution. Okay, guys, I want to do a problem. I just want to, and that's to get to it. That's how I get to this method. Let's just do a couple problems. Okay, let's see here. So here we have, guys, a second order linear DE. I don't know why that corner looks like it's dirty, but anyway, the shadows, when I take pictures of it, end up over there. It's non-homogeneous. The f of x is the x plus 1 e to the 2x. Now, let me point out something to you. We could have done this problem by method of undetermined coefficients. And just for a little practice, and I'll erase it in a minute, but just for a little practice, if I were doing it by that method, what would my guess be? And now, well, I tell you what, let me do one other, let me back up. Let's find the YC first. If I look at the, first of all, this one, I don't have to divide by anything because the coefficient's already 1. So it's already in standard form. So that's good news. I then look at my characteristic equation. So m squared minus 4m plus 4. I factor it. I find out I've got a repeated root of 2. What that'll do is give me YC is C1 e to the 2x plus C2x e to the 2x. Because of the repeated root, I get the x in there. All right, so my Y1 and Y2 are this and this. I'm going to use that in the end. I need that for two things. I needed to write the general solution, and I need it to form the YP that I need. Now, what if I were doing methods of undetermined coefficients? I'm just practice here. What would my guess have been on this? Write down. I want everybody to just take a couple minutes to write down what you think your guess would be on here for your YP. Okay, that's what we were doing the end of last week. All right, so guys, we know we make an initial guess. And this is a guess for YP. This is the last method we did. We know we've got a linear, this thing right here, this x plus 1's linear. So I'm going to put AX plus B. And I clearly need an e to the 2x. Now, that's our initial guess. What's wrong with that guess, guys? Somebody on mic can tell me what's wrong with that. Why it's not the one I need to use, that I can use. Somebody on mic can tell me why.
Because they're included in the YC.
Yeah. Look at this thing. Look at the YC. It had a constant times e to the 2x. There's repetition there. Look at, there's a constant times e to the 2x. There's also repetition right here in the x e to the 2x because there's x e to the 2x there. If I were to bump it up 1, so here's my my second guess. Maybe I'll multiply it all through by an x, ax squared plus bx e to the 2x. Okay? Got to check again. Is that good enough? It's not, it's avoided things here, but it has not avoided the x e to the x term. So my final guess here, guys, is going to be YP. Give me another x, ax cubed plus bx squared times e to the 2x. So I had to make a couple of guesses to get beyond the duplication here. Now, what we would do with that method, we would take this, we would plug it into here, we would match the coefficients, and we'd be on our way. So you decide which one you like better. I'm going to show you how to do this same problem another way by this variation of parameters. Now, the question is always, well, you're going to tell us which method to use. If I don't say, you can use either one you want. But in some way, I'll make sure you know one method and the other method, okay? I'll show you that in just a second. So is everybody okay with this? I'm going to erase it if everybody's okay with it. Is there any question about the guess, about why I made that, had to make 2 guesses there? Or to get to the final answer? Okay, so that's the one, the last one's the one you're going to use. All right, can I erase it? Are we okay? All right, so I'm going to get rid of that. So I got room up here. Now, I'm going to try it this new way. So what's going to go in the Wronskian are the members of the fundamental set. E to the 2x and x e to the 2x. Okay. What goes under that next row are the derivatives of these things. So this one's going to be 2 e to the 2x. And this one I'm going to have to use the product rule. I didn't leave myself enough room. It's going to be 2x e to the 2x. So that's x times the derivative of that, which will be another 2 and an e to the 2x, plus e to the 2x times the derivative of x, which is 1. What's in that Wronskian is the exact same thing that's what's down there. Okay. Now, that Wronskian is not too hard to find. You might even be able to see real easily what it is. I kind of worked it out ahead of time so I'd make sure we got all the right things. But it's pretty easy to see. If you multiply this times this, you'll get this, an e to the 4x and a 2x e to the 2 e to the 4x. If you multiply this times this and subtract, you'll get a minus 2x e to the 4x. So that term goes with that term, so it drops out with that term. You end up with e to the 4x in these things. So the bottom piece of this is e to the 4x. Okay? So that's the Wronskian. What we need in the top, if we're solving for u1 prime, our first variable, I'm going to put 0 f of x in that first column. So 0 x plus 1 e to the 2x. The f of x is this thing right here. And then I'm going to put the same thing I had in the second row, second column of the Wronskian. X e to the 2x, and then 2x e to the 2x plus e to the 2x. Okay, so it's not a terrible determinant here, guys, because notice you got the 0 over here. That's going to wipe out, and then you're going to get x times x plus 1 e to the 4x. All right, x times x plus 1 e to the 4x. Okay, so when I do that, I'm going to get a value, and it's not that hard because this is 0, and then you're going to subtract that. What you end up getting, and I'm kind of running out of room here, is the minus x times x plus 1. So I'm going this way, and e to the 4x. E to the 4x. Oh, I'm sorry. This is a mess. And then it jumped on me. Where'd I go? Okay, so it's, sorry, I'll tell you what, I'll write it up here. It's minus x times x plus 1 e to the 4x. Now, guys, remember, that was a numerator. The denominator was e to the 4x. So the e to the 4x cancels out, and what you get for u1 prime is minus x squared plus x. Okay, minus x squared. I'm sorry, minus x squared minus x. Minus x squared minus x. Okay, now let's look at u2 prime. Remember, the Wronskian is the thing that's below. We already got that. That's the e to the 4x. What we do here is we put the 0 f of x in the second column. So that's going to be 0. And the f of x, remember, is x plus 1 times e to the 2x. It's all it is that thing right there. And then leave the first column the same. All right, of the Wronskian. So it's e to the 2x and 2e to the 2x. Okay. When you multiply that out, or when you find its determinant, it's going to be e to the 4x times x plus 1. So what's in the top there is e to the 4x times x plus 1. Nicely, in that one, the e to the 4x's drop, and you get x plus 1. So it's a matter of finding the Wronskian and using Cramer's rule, in which the Wronskian will appear as a denominator with a determinant, and in the numerator you replace the column with the thing on the right-hand side of the equation. Okay, so I'm more than halfway through. I'm way more than halfway through the problem. Okay, so does anybody have any questions about what I did right there up in that? It's, again, it's not hard to set up. If you know your fundamental set, it's not hard. You got to be really careful with these determinants, but here's what we got. Now, what do we do next? Remember, what we were looking for was u1 and u2. That's easy here. Integrate this. We'll get minus x cubed over 3 minus x squared over 2. You do not need a constant here, guys. The constant would get sucked up in some other parameter. If you integrate this next one, u2, no. Okay, would be x squared plus x. Next to last step. So remember, all you're really getting when you solve that equation by Cramer's rule is the u1 prime and the u2 prime. We still need to find u1 and u2. Remember, our proposed solution was this thing. So my u1 is minus x cubed over 3 minus x squared over 2. So u1 times y1, and y1 was e to the 2x. It's the first member of your fundamental set. The next thing was u2, x squared plus x, times the second member of your fundamental set was x, e to the 2x. Remember, your y1 and your y2 just come from your yc. You can see there that there are some there's some algebra you can do. I suggest you do it, and I'll show you what happened. Does everybody see what I did? I formed the solution once I found u1 and u2. So our big goal with the other stuff was finding u1 and u2, and then form from those two things right there. When I multiplied all that out, I don't know, let me see what I got. I got 1/2. Let's do it right here. Let's make sure we get it. I got 1/2 x squared e to the 2x. I'm just really combining terms here, guys. Minus or plus 1/6 x cubed e to the 2x. Yeah. Technically, you have one more thing to do, and that's write out your whole general solution. That's the yc, which in this case was c1 e to the 2x, plus c2 x e to the 2x, plus your yp, which we just found, which was that. Okay, so that's the end of that problem. Now, I want to do one more, and that's because I just want to review the method, and I want to say that you could not, the next one I'm going to do, you could not do using method of undetermined coefficients. So here's one you cannot use method of undetermined coefficients on. Any questions about the previous thing, guys? A little messy getting there, but the process is really not that hard. Okay. So so here's the one I want to do next. We cannot use the method of undetermined coefficients because the cosecant is not a function that behaves the way you want it to with method of undetermined coefficients. You want to be able to differentiate something that repeats itself. What's the derivative of a cosecant? Anybody? Cosecant of an angle without whatever chain rule. Let's see if we can remember that. What's the derivative of cosecant? Anybody? Might be good that you have a calculus book with you. Derivative cosecant is minus cosecant cotangent. Okay, we can't, it doesn't behave like we want it to use method of undetermined coefficients. So let's go through this one and then we'll probably be about time to finish up. All right, first thing we're going to do, the question that Tiara asked a little earlier, we got to put it in standard form. So the first thing I have to do with this thing is divide through by 4. If you don't do that, it will be wrong. All your determinants will be wrong. All your U1s, your U2s will all be wrong. Okay, they'll be off by some constant factor of whatever that thing you divided by was. So step 1 is divide by 4 here, and I get y double prime plus 9y is a quarter cosecant 3x. The next step is to find my YC. My and go from this form right here. My characteristic equation is m squared plus 9, and the roots of that are m equal plus or minus 3i. Remember that the real part of that is 0. So ultimately you get e to the 0x, which is just 1. times C1 cosine 3x, 3 comes from there, sine 3x comes from there. Okay, so what we've been doing here is building things, guys. The two subjects ago, we were talking about how do you build the YC. Variation of parameters, and this one and the last one, undetermined coefficients, are how to find it if it's non-homogeneous. All right, so there it is. There are my Y1 and my Y2. So step 3 is to form U1 prime. Remember what I do in the bottom? I put the two members of the fundamental set here, cosine 3x, sine 3x, then I differentiate them. So that's going to be minus 3 sine 3x and 3 cosine 3x. Actually, I'm going to go ahead and do it because it's really nice. When you multiply here, you get 3 cosine squared 3x, minus a minus gives you plus 3 cosine squared, or sine squared. So it's 3 cosine squared plus 3 sine squared. Pull the 3 out. 3 times 1 is 3. That Wronskian is just 3. Okay? Just using the sine squared plus cosine squared equal 1 identity. So we've got the bottom part of both of these, U1 and U2 prime. Okay, everybody okay with that being 3? I'm just using I'm crossing over, taking the determinant. This times this, minus a minus will be plus this. Got a nice trig identity used. Okay, what goes in the top is, of the first one, is 0 f of x. 0. Now, here's where you have to be really careful, guys, because it's easy to make a mistake here. Don't go back to the original f of x. You need to, because this really was g of x. You got f of x by dividing through. Make sure you go back to the standard form piece to get that. So this will be 1/4 cosecant 3x. Okay, so that's what you need in that first column. The next column will be what's in the same as that column right there. So sine 3x and cosine 3x. 3 cosine 3x. Sorry. So it's the same as that column. Okay, now actually this one's easy too. Everybody understand how I'm placing things in that top matrix? All right. So look at this. Please pull out your trig when you're doing this because this will make it a lot easier. 0 times that's 0. 1/4 sine times sine times cosecant. Cosecant is 1 over sine. So sine 3x times 1 over sine 3x, just 1. All I get there is 1/4. Now the trig identity. You're going to see a lot of those in here because a lot of those functions that aren't sines and cosines work well with this this method. So that first one is 1/12. Well, okay, it's 1/12. Okay. So that's not so bad. So U1 prime is 1/12. This next one, this time you put the 0 and the 1/4 cosecant 3x in the second column, and then you repeat the first column. So that's what was it? Cosine 3x. And minus 3 sine 3x. Uh-oh, wait a minute, somebody's out. And Allison's got lumped. Okay. Okay. Okay, you're in again, Allison? You okay?
Yes.
All right.
Yeah.
I'm trying to keep an eye on that, guys, because I tend to kind of get wrapped up and not remember. Okay, so when I do this one, remember that this goes in the second column now, and then I repeat the first column. this times this minus this times this. Okay, that's going to be cosine 3x, or 1/4 cosine 3x. 1/4 cosine 3x cosecant 3x. That's times cosecant 3x. Now, guys, let me show you how I want to write that, because that it's a little easier to do that. Let me go up a little ways to get to it. Cosecant is 1 over a sine. So the way I want to write that whole stuff right there is the 1 over the 1/4 will be 1/12 with the 1/3 there. Cosecant is 1 over sine. So I want to write this as cosine over sine. Now, tell me what cosine over sine is. Trig again, please. What's cosine over sine? Actually, it doesn't real. What is cosine over sine? Anybody?
Cotangent.
It's a cotangent. It's cotangent. Okay, so that's cotangent 3x. Okay, so here's what we've got. So u1 is going to be an integral of 1/12 dx, which is 1/12 x. Again, I don't need the plus c's. Okay, I do not need the plus c's. The integral of this one, you might have to go look it up, but I'm going to tell you that I'm going to have the 1/12. Well, okay, what I'm integrating is 1/12 cotangent 3x from all of this stuff right here. Okay. We know if we let u be 3x, we're going to end up with a 1/3 in this. That 1/3 will go with that 1/12 and give you a 36th. The integral of cotangent is actually, to me, it's easier to see from this, because you've got a function in the denominator and its derivative shy of that 1/3 in the numerator. When you've got a function in the denominator and its derivative in the numerator, what is that? You know what the integral of that thing is? If that's a u and that's a du.
Natural log.
Yeah, it's a natural log. So this is natural log of that denominator, sine 3x. Okay. Finally, what I wind up with for my final solution is the general solution is the C1y1, which I think was cosine 3x, plus C2 sine 3x, plus u1y1. There's u1. y1 was cosine 3x. So it was u1 y1, u1 y1, and then u2 y2. u2 was this thing right here, natural log of sine 3x. And my other one was my y2 was sine 3x. So there was my u2 and my y2. Okay, nothing you can do really to simplify that. It just looks like that. Okay, one quick word here, guys, because we are out of time. Try a couple of these, but remember your next stuff on variation of parameters due on Wednesday, so make sure you get that done. Anybody that needs to talk to me about their grade, I will say, at this point, we've got 105 points in homework, okay? I can give you the number of points you've got if you want to email me if you're trying to make this decision about you know, pass, no credit, whatever, I can give you your homework average and your other 2 tests, and I average those 3 things together, and that's what I'm looking at right now for you. Okay, so all you need to know, and I can certainly give it to you, is the sum of some of your homework problems divided by 105 plus the other 2 tests divided by 3. Okay. I said I'd say a little word about Kramer's rule. That might come up, but again, if you want to use Kramer's rule on something like this, look at that coefficient right there, and you put 238 in the first one if you want X, and then you put 238 in the next one, the second column, and then 238 in the third column. If you are doing this in this method, you'll find the Wronskian. This will be third order DE. In the first column, you'll put 0, 0 f of x. For the next thing you want, you'll put 0, 0 f of x, and then repeat the other columns. In the last one, you'll put 0, 0 f of x, and repeat the other columns. Okay, so I think maybe there are 1 or 2 of those in the homework, so you might want to work through one. And they've got a lot of zeros in them, so they're not terrible to do. Question, anybody? I get out of class around, when I get out of class around 2, I've got a telemedicine conference at 3. I'm going to be teleconference to death by the end of this whatever it is, semester. So yeah, I'm going to an orthopedist online. They're going to say, how's your foot? And I'm going to say, it's okay, bye. So, but I hope everybody's doing okay. And if you have any questions or you want to email me, I'll try to get your average back to you as quickly as possible. I should do that late this afternoon, okay? All right, I will see you tomorrow. No, not tomorrow. Wednesday, okay? Bye.